What's going on here? A Geiger counter tells us that an element is emitting one or more kinds of radiation. In fact, this sample is in the process of changing into a new element. For example, in a sample of radon-212, a specific nucleus of radon-212 will emit an alpha particle. Although the exact time at which a given nucleus will undergo this process cannot be predicted. We do know that during a 24-minute period, exactly half of the radon-212 nuclei will emit an alpha particle and transform into a new element, polonium-208. These alpha particles are emitted with enormous energy. But where does all this energy come from? The answer to this question was first suggested by Albert Einstein in his special theory of relativity. Einstein suggested that mass and energy are really two forms of the same thing, and each can be converted to the other. According to Einstein, the equation E equals mc squared relates energy to mass times the speed of light squared, which is an enormous number. So even a tiny amount of mass multiplied by the speed of light squared could be converted to an enormous amount of energy, according to Einstein. By comparison, when a fuel like gasoline is burned in the engine of an automobile, it combines chemically with the air to produce relatively small amounts of energy for travel, along with exhaust products. If the same car could convert the mass of gasoline completely to energy, you wouldn't need an exhaust system because there would be no waste products. Imagine driving up to a service station and saying, "Fill her up, please, with 1 drop of gas." That single drop would take you not just to the next corner, not just to the next city, but it would allow you to drive the car for its entire useful life. Unfortunately, it is impossible to convert matter completely to energy. But that doesn't disprove Einstein's theory. On the contrary, John Cockcroft and Ernest Walton were soon able to provide some experimental evidence. They designed a particle accelerator, which would accelerate protons to a very high speed. They used these protons as a form of subatomic bullet. When they put lithium in the path of these protons, the lithium nucleus was split. The product of the split was 2 alpha particles, which flew apart at high speed. When the mass of the 2 original reactants was compared to the mass of the products had a smaller mass. Just as Einstein had predicted, a small chunk of mass was missing. Calculations supported his theory that this missing mass had been converted to the kinetic energy of the alpha particles. These lost masses are so small, they are usually described in atomic mass units. Protons and neutrons, for example, are slightly heavier than 1 atomic mass unit. In the reaction studied by Cockcroft and Walton, the mass converted to energy is a small fraction of 1 atomic mass unit. Other calculations and measurements of the energy released in radioactive decay all support Einstein's equation. For example, a nucleus like carbon-14 undergoes radioactive decay to produce nitrogen-14 and a beta particle. The mass of the products is less than the mass of the original carbon-14 nucleus. Once again, the mass lost is a tiny fraction of one atomic mass unit. When the carbon-14 nucleus undergoes decay, it is this amount of mass that is converted to kinetic energy, shared by the beta particle and nitrogen-14. In 1939, two Austrian scientists, Lise Meitner and Otto Frisch, identified yet another reaction involving the nucleus. They suggested that when the nucleus of uranium-235 has a neutron fired at it, the uranium atom would split to form much lighter nuclei of completely different elements, while releasing 2 or 3 more neutrons. This newly discovered process, in which the original nucleus was split into 2 main parts, was called fission. The discovery of fission caused considerable excitement in the scientific community for 2 reasons. First of all, when the reactants were compared with the products were lighter, just as they were for radioactive decay. But the missing mass was considerably larger, and so transformed into a much bigger release of energy. In addition, each single neutron would cause the release of 2 or more neutrons during each fission. Each neutron in turn could cause another U-235 nucleus to split, releasing still more neutrons, and so on. In other words, a chain reaction was a distinct possibility. The first controlled chain reaction was achieved in the squash court at the University of Chicago on December 2nd, 1942, under the leadership of physicist Enrico Fermi. More than 3 years later, the first uncontrolled nuclear fission was achieved. The atomic bomb exploded in New Mexico. It proved beyond a doubt that the mass lost by the splitting atoms could add up to a huge amount of energy. But it's not only atom splitting that converts mass to energy. 2 light atoms, both hydrogen, can fuse together to form helium. This process also loses mass. In fact, more mass is lost than in the process of fission. This means more energy is released. It is this fusion process that is believed to fuel our sun and other stars. Nature at least converts nuclear mass to energy in ways that humans find beneficial. In the next program, we will examine how we try to harness this nuclear mass conversion in another beneficial way.